So far we have learned how to build amplifiers using a MOS transistor, the basic common source amplifier, as well as more sophisticated control sources which employ negative feedback. Okay. In most of these cases, the preferred way of biasing the MOS transistor was using a current source, that is to bias a MOS transistor at a given current rather than at a given gate source voltage. Now the question is, how do we realize these current sources? Now we have some idea how to do that. A MOS transistor operating in saturation region itself behaves like a current source, right? So for instance, let's say that we had to bias a transistor. I'll consider the case of source feedback biasing. Then we have a current source I0 over here, which with negative feedback establishes a current of I0 in the transistor M1. Now how do we realize this current source I0? Now there are some ways of realizing a single current source that I won't go into, but at least we know the following. We know the current mirror structure, okay, that is given a single current source I0, we can make many current sources. Okay, this line here going through the MOS transistor means that it's connected to this gate as well as that gate. Okay, so now we can replicate this any number of times and all of them will draw a current I0 as long as they are in saturation region. And we can use one such device to bias this. Instead of this I0, we can have a MOS transistor. It's assumed that these are all identical to each other. Okay, so this will do the job. But the picture is somewhat incomplete because with the transistors that we have, we can only have currents that are being pulled from a node. What I mean is, we don't have a current source of this type where both terminals are accessible to us. Okay, the current is drawn from this node, current is pushed into this node, but both of these terminals are not accessible to us. What we have is a picture of this type where this side of the current is grounded and we can only have currents which are being pulled from some node. Now if you look at the case of drain feedback, the circuit was like this, where this is the supply voltage VDD and current has to be pushed into this node. Okay, we need a current source in this polarity. How do we make that? It turns out that with the kind of device that we have, we already defined this device. This is the NMOS transistor. I used to call it MOS transistor, but it turns out the device that we have been considering so far, which operates with VGS and VDS greater than 0 and current flowing from drain to source, this is known as N-type MOS transistor, or usually it is called the NMOS transistor. Okay. Now with this type of transistor, with an NMOS transistor, it is hard to solve this problem. Okay, it may be done, but it is quite difficult. But thanks to technology, we also have the complementary type of transistor, which is the P type of MOS transistor. Okay, and it's called the PMOS transistor. Okay. Now it turns out that this has exactly complementary characteristics to the NMOS transistor. It is denoted by this symbol, and I'll draw the source on top and the drain at the bottom. I'll explain later why this is the usual convention. And in this case, the current flows from source to drain. Okay, I'll still call it ID, but in case of the NMOS transistor, it flows from drain to source, whereas here it flows from source to drain. And this is the complementary type, and this is quite useful for making current sources of this type. And of course, it's not only useful for making current sources, you can also make amplifiers using that. So what we'll do is now to discuss the characteristics of this PMOS transistor and see how to set up the operating point and how to realize amplifiers using the PMOS transistor. Okay. Just for the sake of comparison, I will put down the NMOS transistor here. This is the drain, gate and source, and we choose the gate source voltage and the drain source voltage as the independent variables while describing the current ID, the drain current that flows from drain to source, and the gate current is 0. This is the NMOS transistor, and in case of the PMOS transistor, again I have drawn the source on top and drain at the bottom, and gate is here. We choose the source gate voltage VSG and the source drain voltage VSD as the independent variables, and that describes the drain current ID which flows from drain to source. So you should know these conventions so that when you write down the current equations, it comes out in the correct direction. Okay. The NMOS transistor, we said, operates with VGS greater than 0 and VDS greater than 0. That is, VGS and VDS are positive in this polarity, and ID is also greater than 0. That is, it always flows from drain to source. And exactly the same is true here. That is, VSG and VSD are greater than 0. So that is, in this polarity we'll have positive voltages. In fact, that's why it's usual convention to draw the PMOS transistor with the source on top and drain at the bottom. Typically, we like to draw circuits in a way that as we go up the page, the voltage levels increase. Okay. Now, this cannot be followed for every circuit, especially when you have AC voltages, alternating quantities, but at least for the operating point, as you go from bottom to top, the voltages will increase. So, in case of a PMOS transistor, the source is at a higher voltage than the drain. So, you draw the source on top and drain at the bottom. And ID, of course, is positive in this direction. I'll continue to call it drain current, but this current flows from source to drain. Okay. Now, if you look at textbooks, there is a variety of choices for describing the PMOS. The NMOS is, of course, always described with VGS and VDS and so on. Now, sometimes the PMOS stuff equations are written with VGS being negative and so on. Okay, but we will stick to this so that all these quantities come out to be positive. As long as you know which direction it is in, it should be fine. Okay. Now, the model of the PMOS transistor is exactly same as the model of the NMOS transistor. The values of the parameters may be different, that's all. So, this ID in a PMOS transistor is 0 if VSG is less than VT. And again, this is technology dependent, but for the most frequently used flavor of the transistor, the threshold voltage is also greater than 0. Okay. And sometimes, to distinguish between the threshold voltage of N and PMOS, we'll start writing VTP for the PMOS threshold and VTN for the NMOS threshold. Okay, they could be different from each other in a given process on the same chip. Okay, so it's a similar phenomenon like in the NMOS. The voltage difference between these two, VSG, has to be greater than some amount for the transistor to turn on. Otherwise, the current will be 0. And it is equal to mu p Cox W by L VSG minus VT times VSD minus VSD square by 2. Okay. And this holds when the transistor is on, that is VSG is greater than VTP and the source drain voltage is less than VSG minus VTP. Okay. And this of course corresponds to the linear or triode region. Okay. You can see that again the equations are exactly the same. Instead of VGS we have VSG and instead of VDS we have VSD. That's all. Okay. And also this parameter we denoted mu p Cox. The mobility of holes or the p-type carriers is different from the mobility mu n of electrons. So this we use a different symbol for. Mu p Cox is different from mu n Cox. It's usually smaller than mu n Cox. Okay. Also in the other region we have mu p Cox by 2 W by L Vsg minus Vt square. Okay, this holds when the transistor is on, of course. Vsg is greater than Vtp and the source drain voltage is greater than Vsg minus Vtp. That is, this corresponds to the saturation region. Okay. So you can see that the model looks exactly the same. The only thing is the parameters are different. Vtp could be different from Vtn and mu p Cox will be different from mu n Cox and usually substantially smaller. Okay. So if you draw the characteristics of the PMOS transistor, they will look similar to the NMOS transistor. Let me take some typical parameters. Let me say mu p Cox is 25 microampere per volt square. Okay, and W by L equals 1. Okay, and I'll take the PMOS threshold voltage Vtp to be 1 volt as well. And with this I can draw ID versus Vsg of the PMOS transistor in saturation region. This is in volts and this is in microamperes. You're already familiar with what the shape looks like. Up to the threshold voltage it will be off and there will be no current, and after that it increases as the square of Vsg, right, or Vsg minus Vt to be precise. And you can work this out for yourself, that at Vsg equals 2 volts we'll have 12.5 microamps of current. Okay, and at Vsg equal to 3 volts it will be 50 microamps. So we'll be here and there and there. Okay, so at Vsg equals 4 volts we'll have 112.5 microamperes. So in saturation region it will be like that. Okay, yeah, I'll just write that saturation region is assumed here. You can also draw ID versus VDS. Okay, and the shape of course is similar to what you see with an NMOS transistor. When Vsg is less than Vtp we have no current in the transistor. When Vsg equals 2 volts the current rises up to 12.5 microamperes and stays there in saturation region. When Vsg equals 3 volts it rises up to 50 microamperes and stays that way in saturation region, and when Vsg equals 4 volts it goes that way. Okay, and this is the boundary between triode and saturation regions. Okay, so essentially everything is exactly the same in a PMOS transistor as in an NMOS transistor. The polarity of voltages are reversed and the current is also reversed. It flows from source to drain instead of from drain to source. And the other thing that is different is the value of the parameters themselves. Okay, this mu p Cox and Vtp could be different from mu n Cox and Vtn. So those things are there, but qualitatively the behavior of the PMOS transistor is exactly the same as that of the NMOS transistor except for reverse polarities. This also means that every circuit that we realized using the NMOS transistor can also be realized using the PMOS transistor. Okay, so that will be the subject of subsequent lessons.